This video is about the topic experimental and theoretical probability. Before we jump into any examples, let's make sure that we understand the difference between an experimental probability and a theoretical probability. An experimental probability is the probability determined on the basis of the results of an experiment that you've repeated multiple times. The theoretical probability is what is expected to happen based upon your knowledge of the situation. Your experimental probability will not always equal your theoretical probability. However, if you run your experiment a bunch of times, over and over and over, it should get very close to your theoretical probability. Let's look at this example. The spinner below shows 5 equally sized slices. Martina spun the dial 1,000 times and got the following results. She had 396 white spins, 419 gray spins, and 185 black spins. So we can see what would happen in this situation. This little spinner, remember like playing board games when you were little, you would spin this around and see where it lands. So for right now, it's landed on white. Okay, but Martina did this experiment 1,000 times, and these are her results. So let's fill in the table below about the experimental and the theoretical probability. From Martina's results, compute the experimental probability of landing on gray or white. So experimental means the results of the experiment, so we use her data that she came up with. And so what's the probability of landing on gray or white? Well, she did this 1,000 times, so our denominator will be 1,000 because that is the number of times the experiment was run. Now, how many times did it land on gray or white? So what we're doing is we're looking at the white column and the gray column, and we'll add those together. 396 plus 419, 19, to get our numerator. Let me kind of fix that. Okay, so what does that equal? 396 plus 419 is going to be 815. So 815 out of 1,000 is the experimental probability. They've asked us to round to the nearest thousandths place, so that is 3 decimal places. And notice that we're already in thousandths, right? 815 thousandths is our fraction, so this is an easy one to convert over, even without a calculator. It is 815 thousandths. Now, part B, assuming the spinner is fair, compute the theoretical probability of landing on gray or white. Now, when it says assuming that the spinner is fair, what we mean is it's just as likely to land on any one of these 5 spots as any of the others, okay? So as we can see, our spinner is built where each wedge seems to be about the same size. And by telling us that it's fair, we can assume that each one is the same size and none of them are weighted differently or anything. Each one is just as likely as the other. Now, what is the probability of landing on gray or white, theoretically? Well, there are 5 total sections of the circle that could be landed on, 5 different slices. And how many of them are gray or white? Well, we have 1, 2, 3, 4. So, 4 out of 5. And if we convert that to a decimal, that would be 0.8. Okay? And what we can see is that our experimental probability is not exactly our theoretical probability, but they are very close. And the more often you perform the experiment, the closer your experimental probability will approach your theoretical probability. Let's do another. All right. This time we are going to roll a dice 150 times, and we've gotten the following results. So let's fill in the table below and round our answers to the nearest thousandths. From Keisha's result, let's compute the experimental probability of rolling a 4. So experimental means based on the experiment, not based on how the experiment is designed and using knowledge of what should happen. We want to show what actually did happen in this experiment. So the probability of rolling a 4. Well, she rolled the dice 150 times. And how many times did she get a 4? Well, it's right here. It told us 19 times. So 19 over 150 is our answer. When we round 19 over 150 to our nearest thousandth, that's three decimal places, we'll get 0.127. All right, now assume that the cube is fair. Let's compute the theoretical probability of rolling a 4. Well, what is going on with this experiment? Let's analyze what's happening. We're rolling a number cube that has 6 sides. We're rolling a dice with 6 sides, and each one should be equally likely because it says assume the cube is fair. So if each of the 6 is equally likely, the expected times you would get a 4 would be 1 out of 6. Okay, that would be how often we would expect to get a 4. So when we put that as a decimal, 1 divided by 6, we get 0.167. Okay, so now notice those aren't exactly the same, but if Keisha were to do this experiment more and more times, her experimental probability would approach the value of the theoretical probability, meaning it'd get really close to it. Let's do one more example. A lottery board is examining a machine that randomly picks the lottery numbers, and on each trial the machine outputs a ball with one of the digits 0 through 9, and then we put the ball back in the machine. The lottery board tested the machine for 150 trials and got the following results. So let's fill the table in below and round the answer to our nearest thousandth. So from these results, compute the experimental probability of getting an odd number. Now remember, experimental means according to the outcomes of the actual experiment. So we want to find the probability of getting an odd number. Well, so let's look at these odds. We have here, 5, 7, and 9. So I've highlighted the situations with our odd numbers. Okay? So our denominator will be 150 because that's how many times we've tested the machine. And our numerator will be how many times we got each of these odd numbers. So 11 plus 20 plus 16 plus 16 plus 14. So we'll add those together real quick. And we get 77, I believe, out of 150. And if we do that division, 77 divided by 150, we end up with 0.513. Okay? Now, assuming the machine is fair, let's find the theoretical probability of getting an odd number. Well, if we're going to get an odd number, how many possible outcomes are there? Well, in total, there are 10 in there, 0 through 9. There are 10 possibilities. And how many of them are odd? Well, 1, 2, 3, 4, 5. 5 of them are odd. So 5 out of 10 are a half. Or as a decimal, we would say 0.5. Notice these numbers are very close to each other. So, and the more this machine is tested, those numbers should get even closer to each other. That 0.513 should get even closer to 1/2. Okay, you could think about this as a way to test and see if the lottery machine is fair or if it's biased towards other numbers. If the theoretical probability, if the experimental probability is not pretty close to the theoretical probability, then something's going on and maybe the machine isn't fair. All right, let's look at part C. Assuming that the machine is fair, which statement below is true? The larger the number of trials, the greater the likelihood that the experimental probability will be close to the theoretical probability. I think that one's going to be true, but we'll read them all to be sure. But notice that it says if you do a bunch of trials, then your experimental gets close to your theoretical. The second one said the smaller the number of trials, the greater the likelihood that the experimental probability will be close to the theoretical probability. That one is false. The more trials we do, the better our experimental approaches our theoretical. And the third one, the experimental probability will never be very close to the theoretical probability no matter the number of trials. That one's also false because we know the more trials we do, the closer our experimental probability should be to our theoretical. So we're going to go with the first one.